Hi everyone, welcome back to my Skin Nutrition Expert series. So today it's very exciting because we're going to be doing a basic chemistry lesson and I can feel you all groaning. But honestly, I'd like to make the case for chemistry because I often get asked questions from therapists like, can I cook in this oil, or is this a better oil to cook in? Or how come some fats are good for my skin and other fats are irritating to my skin? Or even, is butter or margarine better to eat? And all of this can be answered through chemistry. So what I'd like to do is do a really basic chemistry lesson because I'm aware that a lot of people don't like it, and I understand that because I hate physics. So if anyone mentions gravity or electricity, I glaze over. So I thought if we do a basic chemistry lesson, that's going to set you up for understanding the chemistry of fats and oils, and that will set you up to understand why they behave in the way that they do and why some of them are good for us and others not so good for us. So here we go. First of all, there are two important things to remember about chemistry. The first one is everything that we see, everything we touch, even things we can't see and touch, are made up of atoms. And you can probably remember your science teacher telling you this. So I find this amazing, that the difference between the atoms, or the difference between what makes up my clothing and what makes up this whiteboard, is simply different types of atoms. And every atom is basically the same. The difference would be how many protons, neutrons and electrons they contain. So for example, the smallest atom known to man is hydrogen, and it has one proton and one electron. And the largest atom known to man is an element called lawrencium, and it has 103 protons, 103 neutrons and 103 electrons. And in the world of teeny weeny things, that is a big atom. And in between hydrogen and lawrencium are all of the atoms, or elements is another word that they use, that we're familiar with, like oxygen and nitrogen, phosphorus, magnesium, zinc, iron, carbon. All of those sit between hydrogen and lawrencium, and the only difference between them is the number of protons, neutrons and electrons they contain. The other important thing to remember about chemistry is most atoms are not stable on their own. They need to be bonded with other atoms in order to be happy and stable. And these could be atoms of their own type, or it could be different types of atoms. And how many different atoms they need to be bonded to depends on how many free hands they have. So let's give you some examples of some atoms that we find in our nutrition and in our bodies quite commonly. So one of them is hydrogen, and you'll be very familiar with hydrogen, as I said before, the smallest atom of all of the elements. And hydrogen has one hand free, so he needs to hold on to another atom with that hand in order to be stable. So what you often find happening is hydrogen will bond with another hydrogen and you get two hydrogens, so H2, and that's how hydrogen exists in our atmosphere. And then both of these little atoms are happy and stable, they've got their hands held, and it now forms a molecule. Oxygen is another one. Oxygen has two hands free. So with oxygen, he might choose to find another oxygen and they both hold hands like so. Or the oxygen with its two free hands might find a hydrogen and another hydrogen, and you get two hydrogens and an oxygen, which is H2O or water, and it's a happy stable molecule. Nitrogen, he has three hands free. So nitrogen is found in our bodies a lot. Proteins are a good source of nitrogen. And what happens in our body is waste nitrogen often forms ammonia, and that's the smell you get in urine. So it will get three hydrogens, and so it's happy, it's got three of its hands held, and each hydrogen has one of its hands held, so a stable molecule. And then there's carbon. Now carbon is a very special atom. All of our life on Earth is based on carbon, and this is called carbon chemistry. And that's because carbon has an interesting way that it can act. And what it does is it's got 4 hands free, and so carbon dioxide, carbon with 2 di, meaning two oxygens, everyone's happy. This is now a stable molecule. The 2 oxygens have both got their hands held, and the carbon has 4 of its hands held. But another thing that carbon can do is join to itself many, many times. And this is very unusual. You would never find rows and rows of oxygen, but carbon can do that. It can form really long chains or even circles. And this means it can form like a scaffolding or a building block for our body. And all life, whether it's plant life or animal life on Earth, is based on carbon chemistry. So what we're going to be looking at in the next lesson is the carbon chemistry of fats. And as I said before, this will help you understand the way they act and whether or not they are good for our bodies. So I'll see you in the next lesson.